Welcome to our third and final video on dividing polynomials. We're finally going to take a look at the rational zeros test here, and we're going to put it all together and see how all of these different things that we've learned can help us factor polynomials. Okay, so first things first, what is the rational zeros test? Well, it basically just tells us that if we have some generic polynomial, right, and these a's are just the coefficients of each term, and obviously the first and last coefficients can't be zero in this case. So it has to have a constant term at the end. And of course, the first one can't be zero, because if it was, then this would just be the leading term, and we would label that a sub n. That's the only reason why they say it can't be zero. So if we have a normal polynomial that ends in a number at the end, right, has a constant term, and we know that P over Q is some rational number, right? A fancy word for a fraction, in its lowest terms, meaning it's a fraction that's been reduced as far as it can. And it is a zero of this polynomial, then P, the top half of the fraction, is a factor of the last term, and Q is a factor of the first term. What we normally do with this test theorem rule thing is we use it in reverse. We use it to find this number, right? Given this function, we know that we can take factors of this number, factors of this number, create a bunch of fractions from all of those different combinations, and we know that if this function has a rational zero, right, has a zero that isn't an imaginary number, then it's going to have to be one of those that we just found. So let's see what that means in application. So here's our typical polynomial function. We set up our fraction as factors of the constant term over factors of the leading coefficient. Well, factors of the constant term are just 1 and 3, plus and minus, right? And factors of the leading term are 1 and 2, again, plus and minus. So it's going to be 1 divided by 1, 1 divided by 2, right? 3 divided by 1, or 3 divided by 2. And plus and minus, of course, of all those. Because if you have a plus divided by a plus, it's positive. Plus divided by a negative, it's negative. Negative divided by a plus, negative. Negative divided by negative is still plus, right? So you see you get plus and minus, doesn't matter. So those are the only 8 possibilities that we would want to check if we were going to try and factor this thing out. So then we can use the other technique that we've learned, which is synthetic division, and we can start by testing all of those different rational numbers, the plus and minus 1, plus and minus a half, 3 halves, and 3. Now, there's really no rule as to where you start, other than if maybe you have, I don't know, some gut feeling. But remember that if this number was positive, that means the function has a remainder, and it means that it's also the same thing as the function being evaluated is up here above the x-axis somewhere. And then if you tried another number in synthetic division and you got a negative, then it was down here somewhere. And since this thing is a polynomial, in between those two is where you'll find the zeros. So you can kind of chase it down by trying one and then maybe jumping up and trying something else, and if in between it changes, then that's where your zero is. But in this case, we tried 1 and it works, right? We bring down the 2, 1 times 2 is 2, add them 7, 7 minus 4 is 3, goes to 0, and this tells us that this is a rational zero. It also tells us that these are the coefficients of the resulting quotient polynomial. We started with a polynomial of degree 3, so this one is going to be degree 2, right? And so, as it's written here, that's our lower level polynomial. So now our original polynomial f, right, equals 2x squared plus 7x plus 3, that's the quotient, times x, remember it's always minus this number, minus 1. And now if we want to find more zeros of this original thing, all we have to do is try and factor this piece, which is what we do on the next slide. So factoring this, now that we're back to a regular quadratic, we can use the tools that we normally use for quadratics, which is just trying to factor it by observation or using the quadratic formula. But in either case, you can see pretty easily that here's our factors. And then if you checked these numbers, you would again see that the rational zeros still works, right? If we take all the factors of this, which are just 1 and 3 plus and minus, and then 1 and 2 plus and minus, our zeros have to either be plus and minus 3, because that's 3 divided by 1, or plus and minus 3/2. Well, what's the zero that we get here, right? -3 is the number that makes this 0. And what makes this a 0 is 2x plus 1, right? We'd have to put 1/2. And you go, well, how come that doesn't work? Well, because we forgot there's one more. Plus and minus 1/2, right? Because the factors of this are 3 and 1. So 3 and 1 divided by 2 and 1. We forgot about that one. All right. So here are the 3 zeros. But more importantly, this thing factors, right? That is the original function factored out into linear terms. And that's going to be very helpful for a lot of things. Okay, let's put it all together and look at an example. Let's say we were given, because you're probably wondering, why do we bother with all this stuff? Well, let's say you started off with a simple function of 2x squared minus 5x minus 12. And you were asked to set that equal to 0 and solve, which is a very common thing to have to do with quadratics, to set them equal to 0 and solve. Well, the only way to do that is to factor it. Now, if you're good at factoring quadratics, you can kind of do this one by observation. But if you're still learning how that works, you know that it's going to be two linear terms. You know there's going to be an x piece here and an x piece here, and there's possibly some numbers right in front of them. And then there's going to be two constants. We know the product of these two numbers has to be 2x squared, and we know the product of these two numbers has to be -12. Which is why we know that the zeros of this thing, which are going to help us figure out what these terms are, have to be quotients, right, of factors of this and factors of that. So factors of 12, 1, 2, 3, 4, 6, 12. Unfortunately, there's a lot of them, right? These are all plus and minus. I just don't want to write it a bunch of times. And then, of course, factors of 2 are just 1 and 2. So it's either going to be all of these, or it's going to be all of them divided by 2. So 1/2, this is just 1 again, right? 3/2, 2, 3, and 6. So you can see that these are just repeats because we had them up there already. And all that we added was 1/2 and 3/2. So that's still a long list of things to try. But you could now start plugging them in with synthetic division and see which one works. It's going to be a lot faster if you just look at this and go, well, the only combination of this is 2 and 1, right? So now you just have to find factors of 12 that when they're one of them is multiplied by 1 and the other one's multiplied by 2, you get a difference of 5. And by trial and error, 3 and -4. Okay, but the rational zeros is what helps us with that. Let's try one more example with a polynomial that we can't factor by observation because it's not a simple quadratic. So instead we have to rely on all of these things that we've learned. We know that if there is a 0, it has to be factors of 30 divided by factors of 2. So our factors of 30, there are a lot of them, right? And then divided by factors of 2, which would be divided by 1, so it's all the same, and then divided by 2. So 1/2, that's just 1. 3/2, 5/2, that's going to be 3, that's going to be 5. 15 divided by 2, all right, 15/2, and then 30 divided by 2 is just 15. So we have all of these and these fractions. And now it's a matter of doing synthetic division to see which ones are zeros. Well, synthetic division is easy, but it's still not something I want to do with a bunch of fractions, so let's ignore those. And let's just start with some easy numbers. Let's try one. Remember, these are all plus and minus, right? So bring down the 2. And then 1 times 2 is 2. Add 7, right? 1 times 7 is 7. Add to get negative 6. And then a negative 6 gives us negative 36. That's off by a lot. So if that's off by a lot, that means if there is a 0, it's probably not close to 1. It's probably a little bit further away. So instead of moving to 2, right, which is just right next to it, maybe go up by 2 or 3 and try 3 or 5. So let's try 3. So this gives me 6. 6 and 5 is 11. That gives me 33. Minus 13 gives me 20. And then that gives me 60 and 30. And that's even worse, right? That's still way far away. So that seems to be going in the wrong direction. So instead of going up from 1, let's go down. Right? Remember, 1 was still far away, so negative 1 probably isn't good, but maybe negative 2 is. So negative 2 times 2 is negative 4. Add these, that's 1. Right? Then negative 2, add those, multiply here, and lo and behold, ta-da! We found our first 0. And so now we know that our reduced quadratic is 2x squared plus x minus 15 from those numbers there. This tells me, remember, it's x minus that, so that tells me my other factor is x plus 2. And now it's just a matter of factoring this, which is much easier to do this way than to try and do this kind of guess and check way here. And this factors very easily with 2x and x, because we know those two have to multiply by 2x. And then now factors of 15 are just 1 and 15 and 3 and 5. And since the middle number has to be a 1, 3 and 5 are the only ones going to work. These are too big, right? If you put a 15 in here, you're going to get 30 and 1, or you're going to get 15 and 2. So instead, if you put a 5 here, you'll get 5, and a 3 times 2 is 6. Hey, there we go. 5 and 3, and since we want this to be positive, 3 times 2 is 6, minus 5, and there, excuse me, are our last two factors. And in fact, we found all of the zeros. We have the negative 2 that we found here. This one gives us a negative 3, and then this one gives us a positive 5 halves, right? Which we could have found with synthetic division or any of those others, but who wants to deal with fractions? But anyway, that's why we do all this stuff, is all of these different things just give us some clues that help us find these zeros. So we're not just blindly trying numbers. There's some kind of rhyme and reason to what we're doing. All right, hope that helps.